Okay, good morning, everyone. So last time we were talking about spherical harmonics, and so I wanted to go over the logic of this again. And so really what spherical harmonics are is they're a way of summarizing how to transform between two bases for three-dimensional problems. So we have three-dimensional orthobases of two types. One is the position orthobasis, and that we're going to write, or we have been writing, as a tensor product of r cross theta and phi. We're separating out r from the angular coordinates for future convenience, but the elements of this basis describe states where the particle is known to be at some specific position. So particle known to be at the point r, theta, and phi in spherical coordinates. And then we have the angular momentum orthobasis, which we write like this. So it's the same ket r, but now crossed into a ket Lm. So here the particle is known to be at a fixed radius. At r, but it has angular momentum, total angular momentum squared, which is h bar squared times L plus 1, and z component of angular momentum, h bar times m. So either one of these is a perfectly good orthobasis. The position coordinates are a complete set of commuting observables, and so is the combination of L squared and L sub z and the radial coordinate r. They form a complete set of commuting observables. And we need to know how to convert between those two bases. And the answer is given by this inner product, theta phi with Lm. Okay, and that's what we define to be the YLMs. Or in words, we call them, well, sometimes we call them YLMs, but we can call them spherical harmonics. Okay, and last time we wrote down the general formula for these. And we did the lowest few. We just wrote down the lowest few as examples. Okay, and then from that, from completeness, we got a nice formula that allows us to express any wave function in terms of YLMs. Which is nice because that tells us how they decompose into angular momentum states. So in terms of YLMs, which is equivalent to saying, if we know the state ket, we can write it in the second basis, the angular momentum basis. Okay, and the formula had the following form: r theta phi psi, that's otherwise known as the position space wave function in spherical coordinates. That's equal to a sum over all L's, and then a sum over all M's, which go from minus L to L, of a set of coefficients that can depend on the r coordinate times the YLMs. Okay, and then the second part of the formula tells you what the coefficients are. CLMR is I integrate over all angular coordinates. I take YLM theta phi complex conjugate, and then I multiply by the wave function. Okay, so those formulas are complementary. The second one says, given the wave function, we know how to compute the coefficients. The first one says, given the coefficients, we get back the wave function. Okay, so the next thing I'd like to talk about with regard to this is the parity properties of the spherical harmonics. And remember, parity is the operation where you take the spherical coordinate or you take the position and you just reflect it through the origin. So r goes to minus r. So if I draw a picture of this, here's my coordinate system in x, y, and z. Actually, I guess z is up top here. This should be x, this should be y. Okay, and so there's some point that we're describing where it is in terms of its angles and in terms of its radius from the origin. And so if we take the vector r and we replace it by minus r, what are we doing? The parity operator pi is doing the following. First of all, it's taking the radial coordinate r and replacing it by itself. We can't fall into the trap of saying it's taking it to minus r, because when I take this particle and I reflect it through the origin, so it's down here, it's still the same distance from the origin. The radial coordinate is never negative. But what happens to the angular coordinates are theta gets replaced by pi minus theta, which is equivalent to saying that sine theta is being replaced by itself, and cosine theta is being replaced by minus cosine theta. Okay, and the other thing that happens when I flip the position is that phi is getting replaced by phi plus pi radians. And what that really amounts to for our purposes, because the spherical harmonics always have powers of e to the I phi, so that's getting replaced by minus 1 times e to the I phi. So now we can figure out what the YLMs do when we operate with parity. YLM, theta, and phi. And to figure that out, we just have to remember what it's proportional to. So we don't need the different funny normalization factors that come out front of it. This is proportional to e to the I m phi. And there was a factor of sine theta to the minus m.
I'm sorry, Professor. How
Yes.
does phi become phi plus pi?
So we're flipping through the origin. So my phi is the angle at which this point is measured. If I flip it to the other side down here, then the angle is getting replaced. It's just taking phi and moving it by halfway around the circle.
Thank you.
In the XY plane.
Yeah.
Okay. Okay, so getting back to the YLMs. So there's a sine theta to the minus m. I'm not doing parity yet. I'm just writing down, I'm writing down how this thing, or what it's proportional to in terms of angular coordinates. So there were L minus m derivatives with respect to cos theta. And then there was sine theta to the 2L. Okay, and now let's figure out what happens to this thing when we apply these parity operations here. So first of all, the e to the I phi factor, that's saying this is going to be replaced by minus 1 to the m power times itself. So I'll just write the same here. That's not a very good m. Let me replace that. Okay, and then for this factor, sine theta to the m, our little cheat sheet over here says that nothing happens to that, so that's the same. Okay, and here for every cos theta, of which there are L minus m's in that differential, we flip the sign according to this. So this is minus 1 to the L minus M power times the same. Okay, and then the sine theta on the last term here, again, nothing happens to sine theta when we do a parity transformation. So this gets replaced by the same thing. Okay, so under parity, what happens is, we can summarize what happens as the following. Again, nothing happens to the radial coordinate, r, and each YLM in an expression gets replaced by, if we look at what's happening here, there's a minus 1 to the m, and then there's a minus 1 to the L minus m. So that totals just minus 1 to the L times YLM. Okay, and so that says that an angular momentum eigenstate, if I act on it with parity, flips sign if and only if L is odd. So in particular, it's minus 1 to the LM. And so that's our rule for how angular momentum states transform under parity. In particular, they are eigenstates of parity. So that's useful to know. And the angular momentum operators themselves are also eigenstates of parity, which means, remember, for operators, the way something transforms under a parity transformation is like this. You put a parity operator on either side of it, and that's equal to L sub x for the L sub x operator. And that's because L sub x has a R cross a P, R flip sign, P flip sign, so the whole thing doesn't flip sign. And similarly for Y and for Z. In other words, parity does nothing to the angular momentum operator, even though it does do something to the angular momentum eigenstates. And furthermore, just by putting these together, the total angular momentum squared operator is also invariant under parity. So angular momentum is even under parity. Angular momentum eigenstates here flip sign if and only if L is odd. Okay, so last time we also wrote down some of the lowest few spherical harmonics. And I wanted to comment that sometimes it's useful to write down mixed expressions for them. So sometimes useful to have mixed expressions. I'll explain what that means in a second for the YLMs. Okay, and just, it's probably easiest to just give an example. So consider Y10. That was square root of 3 over 4 pi to get all the normalization times cosine theta. But in spherical coordinates, we can write that as z over r. Okay, and similarly for, let's say, y11, what we wrote last time was this is minus square root of 3 over 8 pi sine theta e to the I phi, okay, which we can write out by expanding this exponential here. We can write that as minus square root of 3 over 8 pi sine theta cosine phi plus I sine theta sine phi. And then if you look up in your table of spherical coordinate transformations to rectangular coordinates, that turns out to be minus root 3 over 8 pi times x plus iy divided by the radial coordinate. So I'm using a mixed notation where I'm keeping the radial coordinate, But anytime I see some angles like sine theta or e to the I phi, I convert them into x, y, and z here. Okay, and similarly, if I do y1 minus 1, that turns into, or that equals square root of 3 over 8 pi times x minus iy over r. Okay, so the idea is trade theta and phi for x, y, and z, and then also use r to basically to get the dimensions right, because theta and phi are dimensionless, but x and y have dimensions of length. So anytime I use an x, y, or z, I'm going to divide by r. So let's consider why this would be a useful thing to do. Example. Let's consider a wave function psi of r, theta, and phi, which happens to be some normalization factor times x plus y plus 2z times e to the minus alpha times r, where r is, again, the radial coordinate. Okay, now, I'm not going to tell you what the normalization factor is because it's not going to be needed for what we're going to do. I'm just going to say not needed. And I'm also not going to tell you, I'm refusing to tell you what this wave function is the solution to. In particular, I'm not going to tell you what potential there might be, or even what the Hamiltonian is. Again, because this isn't going to matter for the problem. So what is the problem? The problem is suppose I measure angular momentum. Let's say I measure L squared. Okay, and the classic question in quantum mechanics is what are the possible outcomes that I could get by doing that measurement? And what are their probabilities? Okay, and then I'm going to answer the same question about the operator L sub z. So that's the example that we're going to do here. And the strategy is to take our wave function and write it in terms of spherical harmonics. Okay, so write wave function as a linear combination of YLMs. And it's very important here that we're talking about linear combinations. We don't want products of YLMs because we want to write things as in a basis, which means a linear combination. So not products. I'll explain in a few minutes how that could get you into trouble. Okay, but let's just do this example first. So we have our wave function here, which has this form. And so now what we can notice is that if we take the linear combination 1, 1, minus 1, minus 1 for the YLMs, I'm saving clutter by not putting the theta phi dependence. Okay, but that's square root of 3 over 8 pi, 1 over r, minus x minus iy minus x plus iy. Okay, and so the iy's cancel out. And so what we can conclude from that is that x is equal to square root 2 pi over 3 times the radial coordinate times y1 minus 1 minus y1, 1. Okay, and if you do the similar thing for y, you can discover that y is I square root of 2 pi over 3, radial coordinate y1, 1 plus y1 minus 1. And z is equal to square root 4 pi over 3 r times y1, 0. So we have a list of how to convert x, y, and z into spherical harmonics. Okay, so now if we go back to our wave function that we were given, we just plug in that information. This becomes our unknown normalization factor, square root 4 pi over 3 times r times 1 over square root of 2, 1 plus I, y1 minus 1, plus 1 over square root of 2, minus 1 plus I, y1, 1, plus 2 times y1, 0. Okay, so I've taken care of these funny square root of 2 pi over 3 factors by pulling them outside. And then I have included the 1 plus I, there's an I factor from there. So I put those in. And then for my z, I've put in just the y1, 0. Oh, and I forgot to put in my exponential factor, e to the minus alpha r. Okay, so what does that mean? That means my ket, as opposed to my wave function. By the way, the ket does not come with labels r, theta, and phi. The labels r, theta, and phi go on the wave function. They don't go on the ket. So psi is equal to, though, some radial coordinate function, tensor product, with a bunch of LM states, namely 1 over root 2, 1 plus I, L equals 1, M equals minus 1, plus 1 over root 2, minus 1 plus I, L equals 1, M equals 1. And then for the last one, it's 2 times the state 1, 0. So this is in the LM eigenbasis. Okay, and so now the key thing to answer the question is that all of these spherical harmonics have L equals plus 1. So if we measure L squared, we're guaranteed to get h bar squared times 1 plus 1. So measuring L squared will give h bar squared times 1 plus 1, otherwise known as 2h bar squared, with probability 1. Okay, so that was easy. What's a little bit harder is, but not too hard, is to get the measurements of L sub z, which we pick off from the M value of the different components. Okay, and so from that, we see the possible results for measuring L sub z are, in this case, just the eigenvalues that are appearing in the linear combination, which are h bar and 0 and negative h bar. And so the probability, for example, of measuring L sub z and getting plus h bar is equal to the inner product 1, 1. That's the eigenstate with the state we're in, psi, squared, except then I need to divide by the normalization factor. Okay, we'll figure out what that is later. But in the meantime, this is 1 over square root of 2, 1 plus I, magnitude squared over the norm, whatever it is. So that's 1/2 times 1 plus I times 1 minus I over the norm, which is equal to 1 over whatever the norm is. Okay, so that's not very helpful until we know what the norm is, but we can get the normalization by looking at all the other probabilities and adding them up and making sure that they give 1 in the end. So for example, now, if we do L sub z is minus h bar, that looks like this, 1 minus 1. Okay, and to figure out what that inner product is, we go back up here and we pick it off as the square of this term. Actually, I think I did my ones and minus ones mixed up here. So this should have been minus 1 plus I. Let's see, let's correct this. Okay, but actually it works out to the same value. And here, similarly, this is the square of 1 over root 2, 1 plus I. So that gives the same thing. And then if we ask for the probability of L sub z being measured to give 0, that's equal to 1, 0 psi squared, which if we go back up here, that had a coefficient of 2. And so this is the norm of 2, which is 2, squared, divided by the norm of the state. So that's 4 over the unknown norm. Okay, and now we're going to use the fact that if we add up all the possible things we could have measured, or we could have gotten as a result of the measurement, that has to equal 1, but we found that it's equal to 1 plus 1 plus 4 over the normalization. And so that's telling us that the normalization here is actually 6. And so the probability of getting h bar is 1/6. The probability of getting minus h bar is also 1/6. And the probability of getting 0 is 2/3. Okay, so what happened here is just by knowing how this thing decomposes into spherical harmonics as a linear combination, that tells us how it decomposes into different LM states because they're in one-to-one correspondence. And then even if we don't know anything about how it behaves radially, I'm just putting a function f of r here because it doesn't matter. Okay, then we pick out the probabilities in the end. Okay, so the method I just mentioned would work for any wave function of the following form. Anything that's linear in x, y, and z with any function of the radius only pulled out. So it could have been ax plus by plus cz. And so that's always going to have L equals 1. In fact, the x part and the y part are always going to give you the m equals plus or minus 1 parts. And the z part is always going to give you the m equals 0 contribution to the wave function. Okay, so what about this example? What if the wave function was just a function of r with some normalization factor? And I'll be specific and say it's an exponential fall off. Okay, and I can say or more generally. Just psi of r with no theta and phi dependence. So if you see that, then you automatically know that L equals 0 and m equals 0 for that matter. Okay, and the reason we know that is because any function of r only is equal to y00 of theta and phi, because that's a constant, okay, times something, doesn't even matter what it is. Okay, and right away that tells you that it's only got angular momentum 0 components. Okay, what if we did this? What if we had a wave function that was some function of r times, I'm going to write down a whole list of quadratic possibilities. So some function of, or something times x squared, plus something times y squared, plus something times z squared, plus something else times xy, plus something else times xz, plus something else times yz. Okay, and now the point is one just recognizes that all of that can be written as a linear combination of some YLMs. And if you stare at the YLMs long enough, you'll realize that because it's quadratic functions of x, y, and z, the only linear combinations that will appear are going to be y2 plus or minus 2, y2 plus or minus 1, y2, 0, and y0, 0. So anything with, for example, L equals 1 has odd powers of x, y, and z, so it can't contribute. Anything with L equals 3 or higher is going to give things like x cubed or x squared y or y squared z or something like that, so they can't contribute. So just by knowing how this wave function decomposes into x, y, and z and r, you can pick out what are the possible values of the angular momentum that you can measure. Okay, and so for another example, suppose that we do something even more general, and we say psi of r, theta, and phi is some function of r, and then times anything quadratic. That means including linear terms in x, y, and z. Okay, then you would have also L equals 1. And so you would have L equals 0, 1, or 2 with the appropriate m's. So it goes the other way too. If you know that you have, for example, let's say you know that you're in a state with angular momentum 0 or total angular momentum given by L equals 2, then you know that you can write in the end, you'll be able to write the wave function in that form, because that's the only form that involves those spherical harmonics. And then the other thing I wanted to mention here is, I already mentioned this, but so you might see the x squared and you say, oops, you might see this x squared here, and you might say, aha, I've seen how to transform x into spherical harmonics. And one goes up here and one sees this formula. And you say, all I have to do is square that, and then I'd have products of YLMs. But that's not what one wants to do. When one wants to identify the angular momenta that can occur, you want linear combinations. You do not want products of YLMs, because that does not that does not give you a basis in the sense of linear combinations, which we learned from studying Hilbert spaces before. Okay, so at some point after the midterm, you will doubtless get a homework problem where you need to take some wave function of this form and decompose it into YLMs, and then figure out from the decomposition into YLMs what are the possible angular momentum measurement results and probabilities. And so that was generally how that works. Any questions on that? Okay. All right, so one of the main reasons we like spherical harmonics is because we very often run into, in quantum mechanics, spherically symmetric potentials, for which spherical harmonics are the nicest way of writing things. We can, as I've mentioned, we can write any three-dimensional wave function using spherical harmonics, but it's particularly nice for spherically symmetric potentials, or useful, maybe is a more precise word than nice. Okay, so a spherically symmetric potential means I can write my Hamiltonian in the following way. It's momentum squared over twice the mass. But now I'm going to stop using the letter m for mass, and I'm going to start using the Greek letter mu. And the reason is simply that we don't want to confuse with the quantum number m. So don't confuse with m. Okay, plus a potential, which is a function of the operator r only. So capital R is the operator for the spherically symmetric coordinate r. And so in particular, this potential is assumed to not depend on theta and phi. So when we go back to the isotropic three-dimensional harmonic oscillator and the hydrogen atom, that's the form that we will have. So we have commuting observables, which are Hamiltonian, L squared, and L sub z. Because this thing is spherically symmetric, the action of angular momentum does nothing to it. This thing is invariant under rotations. And so we're going to work in a position basis, or one thing we could do is work in a position basis. Okay, where the kets are labeled by, or let me say, write the wave functions instead. The wave functions are labeled by energy, L, and M. Okay, and I can write that as the inner product of the position eigenstate ket with the state ELM. Okay, and the ELMs are the common eigenstates of these commuting observables. Okay, so E is the Hamiltonian, and L and M are the angular momentum eigenstate labels. Okay, so now the p squared operator is just by definition the sum of px squared plus py squared plus pz squared, which is represented in this basis by I h bar partial x squared plus I h bar partial y squared plus I h bar partial z squared, which is otherwise known as minus h bar squared times the Laplacian operator. Okay, and then we can take this and write it in spherical coordinates. Okay, and so that turns into the following. Minus h bar squared over twice the mass. Okay, that factor times, now I'm going to write the Laplacian in spherical coordinates, which has this form. Okay, there's a 1 over sine theta. I'm going to write this all out, but then it's going to almost immediately go away. Okay, all of that acting on our wave function. Plus our potential now is a function of the radial coordinate acting on the wave function. That's supposed to equal the energy acting on the wave function. Okay, so this is the Schrodinger equation. Okay, and now the point is all this angular ugliness right here we found earlier was minus the operator L squared divided by a factor of h bar squared. Okay, and so that means we can look for eigenstates that have the form psi ELM, which are radial wave functions of R times spherical harmonics, which are going to be solutions to the eigenvalue problem for L squared. Okay, and the point, a good point here is that these things have no M dependence. Okay, and that's because, why is that? That's because when we see this L squared, we can replace the L squared by h bar squared times L plus 1, which doesn't depend on M. Okay, so the reason for no M dependence in the radial wave function is because all of the rest of the problem doesn't depend on M, it only depends on L. Okay, and so now we're going to do that. We're going to take L squared, replace it by h bar squared times L plus 1, times L plus 1, plug it into here, use that to simplify everything. And so what we get is minus h bar squared over twice the mass, 1 over r squared, partial r squared, partial r, minus L times L plus 1 over r squared. All of that acting on our radial wave function times YLMs. That is supposed to equal E minus the potential acting on the same thing. Okay, and now having done that, we can cancel the YLMs from both sides. And all we have is an equation for the radial wave function. Okay, and so in the end, oops, the equation we're trying to solve here is minus h bar squared. I'm just rewriting the whole thing, just for the record. Okay, over r squared. So this is a differential equation that's also an eigenvalue equation, because when we solve it, we're going to be given L. In other words, we're going to consider every possible value of L one at a time, plug them in here, and then we're going to try to solve for the E's. So when I say given L, we really mean consider them all one at a time, each possible value. And we already know what the possible values are. They're 0, 1, 2, etc. Okay, so when we pick up after the midterm on Wednesday, we will be starting with this equation and trying to work out how to solve the eigenvalue problem. First, we'll make some general statements about it, and then we'll start doing various specific examples. The free particle, the particle in a spherical box, etc. Okay, so I wanted to mention a couple of things about the homework that we've seen so far. And one is that I want to encourage everyone to try to be more careful in the future about simplifying things into the simplest possible form. I know sometimes that's not the most pleasant thing to do, but let me just give an example of where this can be useful. Suppose I give you a problem and you're supposed to calculate the expectation value of a position as a function of time. Okay, or a momentum as a function of time. So this has actually occurred in some homework problems we've had. And the thing I want to point out is just those are Hermitian operators. So no matter what the problem is, no matter what the physical situation is, these must be real numbers. Because they're Hermitian operators, their expectation values must be real. And so it's always good form to simplify them into such a way that there's no complex anything within the answer that you've got, no factors of I or anything like that. So people wrote e to the I omega t's, and that's fine, and that's the correct answer, but it's better to simplify so that you've got it specifically in terms of things like cosine omega t and sine omega t rather than e to the I omega t's. Okay, so one can simplify to make it so. An advantage to doing that, or to make it obvious that they are real, is that if you can't do that, that means a mistake happened somewhere, right? And so you can recognize mistakes by the fact that if you calculate something like the expectation value of a Hermitian operator and you don't get a real number, then something went wrong. Here's another example of something that's nice to put in simpler form. Is a few people wrote a Hamiltonian for the harmonic oscillator. You can write it like this. A dagger A plus A dagger. And this is perfectly true. But it's even better to write it like this, as we've done in class. Okay, and so this is even better. And why is it better? It's better because this is normal ordered. So one of the reasons this is important is because the Hamiltonian is not that complicated of an operator, but later on you might have an operator that's more complicated, and there might be more than one way to write it. And sometimes you might have the same operator written two different ways, and it's not obvious that it's the same operator. And so things like canceling things that are actually equal from an expression isn't so obvious. By writing things in normal ordered form, and what that means is every A dagger is to the left of an A. That gives you a standard form, and then you can recognize whether things are equal to each other or not by putting them in a standard normal ordered form. The other thing that's nice is because you have the A on the right, this annihilates the vacuum or the ground state. Which makes it useful for doing calculations. Okay, and then the last thing I wanted to mention is we've had several problems actually with the following theme, where you're given a Hamiltonian, which is a sum of something. I'm summing over k times the momentum squared plus something else. I'm going to call this something else anything times xk squared. So this is maybe after a rotational change of coordinates, or some change of coordinates, or change of variables. But the thing that was supposed to be a theme from all the homework problems is that anything of this form is a sum of harmonic oscillators, and therefore you can immediately write down what the energy eigenvalues are and the creation and annihilation operators are and all that stuff. And the way you do that is just whatever something is for each k, you interpret that as 1 over twice the mass of the corresponding particle, and whatever anything was, you interpret that as 1/2 the same m sub k of an angular frequency squared. Okay, and then by doing that, you get the effective masses and the effective angular momenta, or sorry, not angular momenta, angular frequencies. And that gives you your AK daggers and your AKs, and that gives you your energy eigenstates. So for example, if you go on to study quantum field theory, you find out that basically you're just doing all this all day long. You're taking dynamical variables, you're writing them as a sum of Hamiltonians of this form, and then you're working out what the energies are by writing it like this. So notice that for each k, there's a something and there's an anything. And then what you're doing is you're taking those two quantities and you're trading them for a mass and an angular momentum. Okay, so that was the general theme that all of those problems are supposed to illustrate, and you will doubtless see this again. Okay, so Monday, Monday you have your midterm. Okay, the information is on the course webpage, but again, it's the same thing as what we had last time. So I will see you all then, and I'll be happy to answer any questions you might have about anything up till now. Okay. All right. Any questions? Okay, if not, then I will